Chapter 2. Acclimation to Huge Immensity. Incredibly large and powerful objects exist in the universe. As a class, the largest and brightest single objects are star-like radio sources called quasars. An example is quasar 3C273, estimated to be about a light year across and to produce energy equivalent to about 10 trillion suns. This object is located so remotely that its signals traveling at the speed of light require about 30 million centuries to reach Earth. Indeed, the universe is a place in which huge immensity abounds. Memory of this characteristic is essential when shifting thought from familiar terrestrial physical sizes to unfamiliar extraterrestrial ones. Being only about 1/1000th light year across the outermost planetary orbit, our solar system is small compared with the size of quasar 3C273. Yet spatially, the solar system is quite immense. For example, the distance between the Sun and its outermost planet Pluto is 3.7 billion miles. Sunlight requires about 5.5 hours to journey there, and a spacecraft traveling at only 34,000 miles per hour would require one quarter of a decade to make the same trip. In the solar system, 9 planets orbit the Sun. These bodies are enumerated in Table 1 to illustrate comparative size and position. In Table 1, Mercury, Venus, Earth, and Mars comprise the inner planet group which orbits nearest the Sun. Jupiter, Saturn, Uranus, Neptune, and Pluto constitute the outer planet group. An asteroid belt not included in the table lies between the Mars-Jupiter orbits and serves to mark separation between the two groups. Diameters of all the inner planets are less than 1% that of the Sun. Earth slightly outranks Venus in size, with a diameter of nearly 1/100th, 0.92%, that of the Sun. Except for Pluto. All planets in the outer groups have diameters greater than 3.6% of the Sun's. Of all planets, Jupiter is the largest, with a diameter slightly exceeding 10.1%, that of the Sun. Saturn is second largest, with a fractional comparative diameter of 1/11th, 8.7%. An appreciation of the relative spacing of the planets and respect to the Sun can be obtained by noting time for sunlight to be received. Inner planets receive light from the Sun ranging from only 3 to 13 minutes, 0.05 to 0.21 hours. In contrast, outer planets receive light ranging from about 3/4 to 5.5 hours, as between Earth and Saturn, the time differential for a light signal is almost 1/4, 1.32 minus 0.14 hours. This time corresponds to the shortest orbital distance between the two planets of 8.55, 9.55 minus 1 astronomical units, or 794.3 million miles. By Earth standards, the approximate 800 million miles to Saturn is an immensely large distance. Voyager 1 traversed approximately this distance and took over 3 years and 2 months to do so. Voyager 2, on its journey to Saturn, traversed about 1.4 billion miles, a journey requiring slightly more than 4 years. Historically, these accomplishments are superb. However, limited speed and load carrying capability of 20th century spacecraft preclude extensive excursions in or beyond the solar system. Significant improvement in this restricted ability to travel extraterrestrially awaits the application of nuclear power to spaceflight propulsion systems. Technological limitation is not the only impediment to space exploration. There is also the problem of sustained economic support for long, expensive spaceflights. These severe restrictions suggest strongly that more should be expected from spaceflight than extensive data generation. Data analysis are the key. Analyses must be directed towards pinpointing, in a timely manner, specific worthwhile objectives for succeeding flights. A long wait, say 10 years, before data from a flight are digested comprehensively does not permit plans for subsequent flights to benefit very much from prior experience. Apropos, 6 years after launch, Voyager flights returned to compelling reasons for undertaking further flights to Saturn or to any other part of the solar system. The purpose of this treatise is to demonstrate that compelling reasons indeed do exist for urgent further exploration of Saturn and environs. Therefore, let us focus now on the Saturnian complex and concentrate attention there. Since the Galilean period, nearly 400 years ago, Saturn's most notable feature has been its rings. These rings span 22 Earth diameters and extend on either side of the planet an equivalent of 1.13 Saturn diameters. Sufficient consistency in plan form of the ring plane has been displayed over time, such that designations could be assigned to various regions. Starting from the outer edge of the ring plane and progressing inward, 4 rings have been designated: A, B, C, and D. A narrow separation occurs in the outer extremity of the A ring, called the Encke division. After the discoverer Johann Encke, the A and B rings are considered non-contiguous, being separated by a space called the Cassani division after the Italian-born French astronomer. The inner edge of the B ring also constitutes the outer edge of the C ring. The D ring fills a space from 1.1 Saturn radii to the inner edge of the C ring, a ring having a so-called crepe texture. Additional radio designations are not consecutive, owing to the chronological order of discovery. For example, before Voyager 1, a faint ring located between about 3 and 8 Saturn radii had been assigned the next alphabetical designation, E. Then Voyager 1 found 2 rings between the A and E rings. These latter 2 rings have been designated F and G, with the F ring being innermost. Photographic imagery from Voyager 1 has credited Saturn with 15 satellites or moons. Voyager 2 added several more. Of the entire total, only 8 are spherical bodies, the remainder all being irregularly shaped, enumerated in progressively outward orbital locations from Saturn. The spherical satellites are Mimas, Enceladus, Tethys, Dione, Rhea, Titan, Iapetus, and Phoebe. The first four, Mimas, Enceladus, Tethys, and Dione, lie within the radial expanse of the E-ring. Rhea, at 8.7 Saturn radii, orbits closely outside the E-ring outer edge, 8.0 Saturn radii. Titan, Iapetus, and Phoebe are quite remote, being at about 20, 59, and 215 Saturn radii, respectively. Practically all irregularly shaped satellites occupy the zone between the A and G rings. Two of these, 1980S27 and 1980S28, are unique in that they orbit tightly astraddle the F ring. This particular pair has been designated shepherding satellites. Saturn's rings and spherical satellites are summarized pictorially in Plate 1, Parts A and B. Part A shows the relative spacing of the rings with their classical nomenclature. Part B shows spherical satellites in their relative orbital spacing. Mimas, Enceladus, Tethys, Dione, Rhea, and E-ring are close to Saturn compared with the outer satellites Titan, Iapetus, and Phoebe. Considering the Saturn system boundary defined by the orbit of the outermost satellite Phoebe, the system diameter is 26 million kilometers, 16 million mi, also equivalent to 0.17 astronomical units. The system span measures about half the distance between the Sun and the innermost planet Mercury, 0.39 AU. Saturn is an order of magnitude larger than Earth, yet Saturn is regarded with wonder and astonishment, not because of its large size, but because of perplexity aroused over its dramatic rings. A widely held popular view is that ring divisions are always located in the same place. This mythical view persists despite observational reports indicating significant variability in ring division location. An exemplary case in point is the Encke division. After Professor Encke's announcement concerning discovery of a gap in the A-ring, some observers could not find the alleged separation at all. Others who succeeded reported the gap located at various distances inboard of the A-ring outer edge. Distance of the Encke gap inboard from the A-ring outer edge can be expressed non-dimensionally as a fraction of the entire A-ring radial width. Fractional distance locations of the Encke gap inboard of the A-ring outer edge show appreciable variation as follows: 0, 1/4, 1/3, 2/5, and a half. According to these data, constancy of location within the A-ring definitely is not an attribute of the Encke gap. There have also been indications of other variations in ring geometry. Different ring plane thickness values have been reported as well as different values for width of the Cassini gap. Cassini gap width variation, as much as 33%, reflects time variant radii for the ring outer edge and the A-ring inner edge. An impression is conveyed that latest reported measurements purport to be the true ones when, in reality, all might be quite nearly correct at time of observation. General reluctance to accept variable ring system geometry occurs because of apparent failure to identify a physical mechanism suitable for producing recurrent change. Presented in Plate 2 is a photograph of Saturn exhibiting circularly complete rings. The elliptical appearance of the rings is due to the angle at which the ring plane is viewed, near the ends of the major axis of the ring eclipse. The NK division can be identified by a short, dark arc. By scaling the photograph along the ring major axis, the NK division is found located a fractional distance of 1/5 the A ring width from the ring outer edge. This value is at the low end of the historical range of reported values. Separation of the A and B rings by the Cassini division also is evident in Plate 2. This division shows as a clear space across the face of Saturn, then as a dark and broad continuous arc throughout the remainder of the ring. Ratio of the A ring breadth to the B ring breadth scales 3 to 5. On the same scale, Saturn is 21.6 units in diameter. For an equatorial diameter of Saturn equal to 120,660 kilometers, apparent width of the A and B rings is about 16,750 kilometers, 10,400 miles, and 27,930 kilometers, 17,315 miles, respectively. Distance of the NK division from the A ring outer edge is calculated to be 3,350 kilometers, 2,080 miles. Obviously, large distances photographically are compressed into an exceedingly small space. The ring illustrates well this high degree of compression. Width of the A ring is equivalent to about an 18-hour non-stop jet flight between Montreal, Canada and Melbourne, Australia. Yet in the photograph, this great distance is represented by only 6 to 10 centimeters, 1/4 of an inch. Mental cognizance and retention of this high compression characteristic during examination of subsequent photographs is helpful to their comprehension. Part 2. Saturn the Stronghold.